The atmosphere of the Earth is divided into 4 layers. So when you guys are doing the atmosphere of your planet, reporting about that, one of the things you need to also tell us is how many layers it has, and then what's the properties of those different layers. For the Earth, we got the troposphere. So a picture like this would be a good one to go with that. Usually you'll find pictures like this on the internet. It will show you the layers of the atmosphere. Troposphere here, it's the lowest layer. Okay, troposphere. So is the layer that we live in, and basically extends up to the clouds about 25 kilometers in elevation. So when airplanes are going in the air, most likely they are in the troposphere, okay? So basically they go up to here, okay? Now, one of the things that graphs like this will also show you is the temperature, how the temperature varies. You see the red line? And how the pressure varies. I drew the pressure here, starts here, and goes all the way there. So I'll talk about that in a little bit, what that means. Stratosphere is the layer above that. So we have stratosphere from here to here, okay? And we can see the ozone layer, O3. The ozone layer is inside of the stratosphere. So it's the layer above that and contains the ozone layer, and it is 40 kilometers in elevation. So from here to here is 25, from here to here is 40, okay? So basically, by the time you get here, what's 25 plus 40? 65, right? So they're 50, 60, 65. So that's getting us roughly to an elevation of 65 kilometers, which is about 40 miles, okay? Mesosphere is the layer above that. So then we got mesosphere, this one here, the third layer, okay? And it helps to burn up most of the meteors that fall to the Earth, okay? When a meteor is falling through the Earth, most of it burn up in the mesosphere. A lot of times we see it and we call it a shooting star. A meteor is not a shooting star. Very, very bad term. Shooting star, it has meaningless. It's just a meteor that's burning up in the sky. Okay, the meteor mesosphere is 35 kilometers in thickness. So 35 plus the 65, that's getting us to 100 kilometers. You see here? 100 kilometers. So the total elevation is now at 100 kilometers. And then after the mesosphere, we got the ionosphere. Ionosphere is the outermost layer, and it itself is 30 kilometers from here to here. So 100 plus 30, now that's taking us to 130 kilometers, okay? The total sum of all of that, 130 kilometers. So roughly, in terms of miles, that's about 80, 90 miles. The easy way you can remember it, just to not make it complicated, the whole thing is about 100 miles, okay? So if anyone were to ask you, how much is it till we get to pretty much outer space? It's 100 miles. That's not that much, is it? Weird. It's pretty weird. On the surface of the Earth, 100 miles is nothing. From LA to San Diego is like 80, 90, 100 miles or 120 miles, you know. So along the surface of the Earth, 100 miles is not a lot. But if you go vertical 100 miles, you're already in outer space, right? And remember that guy, he went up and he dove from up there. There's a video on it. So he went up, I believe, pretty much to outer space, and then he just fell from there. He did a dive. Amazing. So he went up about 100 miles or so. He went up to the top. Then from there, he dove all the way down. Okay, so now, the temperature of the layers winds like a snake. So that's what this one is, the red line. You see here? It's kind of like a snake type thing. What does this mean? So let's interpret that. The temperature of the troposphere ranges from 300 Kelvin to 200 Kelvin. So if we put this, see how the red line is doing this? So what that means is when I'm at the surface of the Earth, the temperature starts out at about roughly 300 Kelvin. Okay? So at the surface of the Earth, the average room temperature is 300 Kelvin. 300 Kelvin, the Kelvin scale is the Celsius plus 273. So if we're talking 300 Kelvin, how much Celsius is that? 27 Celsius. So an average comfortable room temperature is 27 Celsius. How many Fahrenheit is that? About 82 Fahrenheit. So when you hear astronomers say 300 Kelvin is the temperature of the Earth, that corresponds to a kind of a room temperature of 80 Fahrenheit or so, about 25 Celsius. So that's basically room temperature. Now, as you go up in elevation, so let's say you go up to this elevation, you go across, you go down, and that will tell you how cold it is. So basically, when you go to the top of the mountain, and you go a little bit above that, you see, a little bit above that. And if I want to know how hot it is, look how hot it is. That's 200. It looks like from the chart, that looks like about 220 Kelvin. So by the time you go to the top of the mountain and even higher, you're already at 220 Kelvin. And how much Celsius would that be? 220 minus 273. Negative 53 Celsius. Is that cold? Yeah. Okay. So if you are in an airplane and you touch the window, is it cold? The airplane window? If you get a seat next to the window and you touch it, oh yeah, it's cold. Don't try opening the window because it's going to be really cold. Plus, the pressure outside is going to be less, right? I'll talk about that in a second, the pressure graph. So if you keep going up higher, higher, by the time you get to here, you see, by the time you get to the top of the stratosphere, you see how cold it is? Now it's even less than 200, maybe 200 or 190 or something like that, 190 or something. So basically what this is saying is the troposphere ranges from 300 to 200 Kelvin. You see, that's the troposphere. So by the time you get to the top of the troposphere or the bottom of the stratosphere, it's about 200 to 190 Kelvin, very cold, okay? Now after that, the temperature kind of goes up again. So by the time you get to, let's say here, you go across, you see this is the ozone layer? Now you go down, what has happened to the temperature? It's warmed up again a little bit. Now it's 200, 210 Kelvin, 220 Kelvin. You see, so the next part here says the stratosphere ranges from 200 back up to 230 Kelvin. So that's how to interpret this, you see. That means as you go up here, it's warming up. Why? Well, we know the ozone layer helps to absorb X-rays, right? Gamma rays, very energetic rays. So that's why the ozone layer is actually hotter than the layer right below it. Okay, so the temperature is increasing again. So the stratosphere ranges from 200 to 230. This is because it absorbs the energy of the sun and it gets trapped there. We call that the greenhouse effect, right? Then after that, then it starts cooling down again. You see, so by the time you get to here, this elevation, that's about as cold as you're going to get. You go down, you see? That's really, really cold. So the mesosphere cools down again to roughly about 180 Kelvin. 180 Kelvin is very cold, okay? So again, you see, you want to put here 180 Kelvin. That's roughly Celsius, 180 minus 273, about negative 90 Celsius, you see? So then what happens after that? The temperature, the ionosphere heats up to about 300 Kelvin. So you see here, cools down, heats up, cools down. Now by the time you get to here, it heats up again. Well, that's actually not surprising because by the time you get to here, you're getting the direct rays of the sun. So it's actually kind of hotter than the lower layers, you see. So then you have the ionosphere heats up to about 300 Kelvin. This is because it receives the direct rays of the sun. So you will have similar graphs like this for your own planet that you're doing report on. You will have the temperature varies in some weird way, and then you can tell us about that. Now, the other graph that you see here is the black line that I've drawn. And the black line is illustrating, it's a different scale. The black line is illustrating how the air pressure changes as a function of elevation. When you are at sea level, what's the air pressure? 760 millimeters mercury. 1 bar, 1 atmosphere. This is called the pressure at sea level, okay? When you go in the sea, if you go in, the deeper you go, the sea level pressure starts increasing. So if you go quite deep enough, you can get to 50 atmospheres, 60 atmospheres, 90 atmospheres, 100 atmospheres, you know. But what happens to the air pressure as you go up? The air pressure starts decreasing. Why? Because the air gets thinner. You don't have as much air up there, and it gets thinner. The other thing, the reason the pressure decreases, because as you go up, there's less air above you, okay? The more you go up, there's less air above you pushing down on you, you see? So when you're at sea level, you got all of the atmosphere of the Earth pushing down at you, you see? The more you go up, less air above you pushing down at you. So that's a good reason why the pressure decreases, you see? So you go up here, let's say to the top of the mountain, and you go down, the pressure has already decreased, okay? So when you go to the top of the mountain like Big Bear or something, air pressure there is less than the pressure on the surface, right? If you're boiling an egg, cooking breakfast or something, it's going to be easier to boil water over there than on surface, right? The temperature, the boiling point of water is going to drop because there's less air pressure. So you have to cook the egg longer. Okay, if you cook it like the same time that you cook on the surface, then it's going to come out and it's not going to be boiled well. It's not going to be hard. You have to cook, you have to keep it longer. Okay, that's also the other reason that when a basketball team goes to Denver Nuggets and plays there, they have a hard time, right? There's less air pressure there. There's less, not only less air pressure, but there's less air. You see, the air is thinner up there, so it's harder for you to breathe and to maintain your pressure in the lungs, right? So what's happening, therefore, as you go up, 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 up? So basically, by the time the pressure goes here, kind of where the airplanes are, you see here, the air pressure is decreasing. So that's actually the more important reason why don't open the window in an airplane, okay? Not only is it cold outside, but that's not even that important. The pressure outside is less than the pressure inside the airplane, right? If you open the window, what's going to happen? The greater pressure inside the plane will push you out to the less pressure outside, okay? It's not that the less pressure is sucking you out, it's the greater pressure inside pushing you out, okay? So by the time, basically what's happening to the pressure, it never comes back, you see? It just keeps getting less, 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 less. By the time you get to the outer space, there is no air above you. So we expect that by the time you get to outer space, the pressure is 0 bar, means 0 atmospheres, you see? So by the time you get there, you should end up basically at this corner. And that should be 0 atmospheres, you see? So that's what's going to happen to the pressure. So the temperature is doing this thing, and the pressure is doing this thing, okay? So you're going to have something similar like that for your own planet.